Imagine watching a sequence of events unfold over time. A machine might fail. A stock market might crash. A communication error might occur. Or a detector might falsely register a photon. If these events are rare, but there are infinitely many opportunities for them to happen, can they continue happening forever? The Borel-Cantelli Lemma gives a remarkable answer. Suppose we have an infinite sequence of events, A1, A2, A3, and so on. Each event might represent something happening at a particular time. It could be a machine failure, a stock market crash, a communication error, or a false click in a photon detector. Now suppose the sum of all their probabilities is finite. In other words, if we add the probabilities together, the total does not grow without bound. The question is, can infinitely many of these events still occur? Think of probability as a limited budget. Imagine beginning with $1. The first event uses 50 cents. The next uses 25 cents. Then 12.5 cents. Then 6.25 cents. The process can continue indefinitely, but the total amount spent never exceeds $1. This is the intuition behind the lemma. If the total probability assigned across all the events is finite, there is not enough probability mass to support infinitely many occurrences with positive probability. To prove this, we introduce a sequence of tail events. For every positive integer n, define Bn as the union of an plus 1, an plus 2, and everything after that. Bn means that at least one event occurs at or after time n. For example, B5 asks whether anything happens from event number 5 onward. Each time n increases, we ignore more of the past, so the tail events become smaller. B1 contains B2, B2 contains B3, and so on. Now comes the key idea. Suppose an outcome belongs to every tail event. That means there is an occurrence after event 1, after event 10, after event 100, after event 1000, and no matter how far into the future we look. The only way that can happen is if infinitely many of the events occur. Therefore, the intersection of all the tail events is exactly the event that an occurs infinitely often. If the events eventually stop, the outcome will fail to belong to some sufficiently late tail event. Next, we estimate the probability of a tail event. Because Bn is a union of all events from time n onward, the union bound gives P of Bn is less than or equal to the sum from k equals n to infinity of P of ak. The expression on the right is the tail of the original probability series. Because the full series converges, these tail sums become smaller and smaller as n increases. Eventually, they approach 0. So P of Bn must also approach 0. Now apply continuity of probability for a decreasing sequence of events. Since B1 contains B2, B2 contains B3, and so on, the probability of their intersection equals the limit of P of Bn. But we have already shown that P of Bn approaches 0. Therefore, the probability that an occurs infinitely often is 0. This is the first Borel-Cantelli lemma. Notice that this direction does not require the events to be independent. Consider a sequence of annual credit loss events monitored by a bank. As debt is paid down, savings increase and financial conditions improve. Suppose the probability of a serious default event becomes smaller each year. For example, 5%, then 2.5%, then 1.25%, and so on. These probabilities form a convergent series. The Borel-Cantelli lemma then says that the probability of such default events occurring infinitely many times is 0. They may occur once, or even several times, but with probability 1, only finitely many occur. The key condition is not simply that each event is rare. The sum of all their probabilities must be finite. Now consider a sequence of quantum optics experiments. A pulsed laser emits photons, and a detector occasionally produces a false click because of background noise. Suppose each new generation of the detector reduces the false click probability 10%, 5%, 2.5%, 1.25%, and so on. The sum of those probabilities is finite. The Borel-Cantelli lemma tells us that false detections do not continue infinitely often. They may happen occasionally, but with probability 1, only finitely many false clicks occur across the sequence. The Borel-Cantelli lemma captures a simple but profound principle. If the total probability of a sequence of events is finite, then those events cannot occur infinitely often with positive probability. Whether we are studying machine failures, financial risk, communication errors, or quantum detectors, the same idea applies. A finite total probability cannot sustain infinitely many occurrences.